Now forget about pulses. If we want to talk about waves, we have an equation called the universal wave equation. We remember before, for the pulse, we have the length of the wave equals the velocity by delta t. But now we talk about wavelength represented as lambda. That would equal the velocity by the period. That's when we are talking about wave. So if you want to convert the pulse equation to wave equation, the length will be the wavelength lambda equals the velocity is the same, but the delta t would be the period in this case. So for a periodic motion, you have the period as 1 over frequency. And if you replace the t with 1 over frequency, then the equation would be over here, lambda equals v over frequency. So in this case, the velocity of the wave would equal the frequency by the lambda, and that is what is known as universal wave equation. Example on that: to generate a wave in a stretched spring, you oscillate your hand back and forth at a frequency of 2 hertz. So that's the frequency. If the speed of the wave in the spring is 5.4 meters per second, what is the wavelength? We have v and we have frequency. What is the wavelength lambda? We know that the v equals frequency by lambda. Lambda equals v over frequency. We have v as 5.4 over 2 as a frequency. That would give you the lambda or the wavelength to be 2.7 meters. So far we talked about a single wave or a single pulse. What if you have more than one wave? In this case, if you have more than one wave that are moving against each other, then in this case you have something called wave interference, or in other words, it's called as superposition. So you have pulse A going to the right direction and pulse B going left direction. At the moment where they hit each other, these two pulses will interfere, and you have a final or total wave that would be called as the superposition wave or the interference wave. That case could happen when you have two people talking to each other. Each one of them will be having their sound, because the sound is made out of waves. So those waves will interfere to each other, create a new total wave that is called interference or superposition wave. So the interference can be defined as the effect of two pulses or two waves crossing within a medium. The medium takes on a shape that is different from the shape of either pulse alone. So you have this pulse looking this way at a certain wavelength, and you have this pulse looking in another way. The total pulse will be this total curve over here. So in this case, the new pulse or new interference wave is different than both waves making that interference wave. So to define the principle of superposition, it is the displacement of the combined pulse at each point of interference. That would be the sum of the displacement of the individual pulses. You have pulse A going in a certain direction and pulse B going in the other direction. There is a total pulse or a total wave that is called the superposition or the interference wave. Now there is some waves, when they combine or interfere to each other, they will add up and create a new shape. In this case, we call it constructive interference. That's when you overlap the pulses to create a pulse of greater amplitude. So pulse A is coming in from the right, pulse B coming in from the left. Then you create a higher new pulse with a higher amplitude. That's called constructive interference, because it combining those two pulses created a higher amplitude. While some waves, they cancel each other or they reduce the amplitude of the total pulse. That's what we call destructive interference. That's when you overlap two pulses or more, you create a pulse that have a smaller amplitude. So you call it destructive interference. So the displacement of combined pulse at each point of interference is the algebraic sum of the displacement of the individual pulses. This sum could be adding up to create higher amplitude, or could be creating a lower amplitude. That's where you define either a constructive interference or a destructive interference. Now, what would happen when you have the pulses reflected? You have more than two pulses or more, and they are combined together, but they reflect through a barrier for a fixed spring. That spring having one side fixed. So we know that for a single wave or a single pulse, it will hit the wall and it will have inverted pulse. What if you have two pulses, pulse A going to the right, pulse B to the left? You have overlap region here, and you have the interference wave or interference pulse. Now you have the total pulse in this case would be looking like this. And when the pulses are inverted with respect to each other, overlap, the displacement of one pulse is reduced by the displacement of the other pulse. So at any point in the region of overlap, the displacement of pulse B reduce the displacement of pulse A to produce the resultant pulse, and it would be a destructive interference in this case.